We have this strangely persistent idea in medicine that in order to fix something, you first have to completely destroy it.
Right. Yeah, the whole tear it down to build it up mentality.
Exactly. It's a bit like a controlled burn in a forest, you know?
Yeah.
You scorch the earth, you clear out the deadwood, and you just sort of trust that the ecosystem is going to aggressively rebuild itself. But, I mean, what if that forest is already depleted?
That is exactly the problem we run into, especially in aesthetics.
Right. So, welcome to the deep dive. Today, we are looking at a massive paradigm shift in regenerative medicine. We're getting into what happens when you combine the intentional controlled burn of a cosmetic laser with a localized flood of highly purified salmon DNA.
Which sounds completely bizarre, I know, but we're essentially moving away from just relying on the injury to force a result.
Yeah.
Instead, we are looking at how we mathematically fuel the recovery at a cellular level.
Yeah, like changing the physical architecture of the skin before the damage even occurs. And to get to the bottom of this for you, we are pulling from a highly specific stack of sources today.
Very specific.
Yeah. We have clinical trial reports on severe scar treatments, advanced aesthetic clinic protocols, and we're even digging deep into the National Center for Biotechnology Information's genetic database.
Specifically focusing on something called the HSPA4 gene, which is fascinating.
It really is. So our mission for you on this deep dive is to understand the exact biological mechanisms at play here. We want to unpack why mechanically injuring the skin while simultaneously feeding it these specific polynucleotides creates this biological synergy.
Because it doesn't just heal scars. It fundamentally alters how human tissue responds to trauma.
Okay, let's unpack this. Let's start with the trauma itself. To understand the repair, we really need to understand the crisis we are engineering, right? Why are we using lasers to damage the skin in the first place?
Well, the engineered crisis relies on energy-based devices, or EBDs. In the source literature, we are primarily looking at two distinct tools.
Okay.
There's the non-ablative Erbium.YAG laser, which operates at a 2,940 nanometer wavelength, and then the fractional carbon dioxide, or CO2 laser, operating at 10,600 nanometers.
And those specific wavelengths, they aren't arbitrary, right?
No, not at all. They are chosen because their specific target in the tissue is water.
Right. And given that human skin cells are mostly water, the laser is effectively, what, flash boiling the moisture inside the tissue?
That's exactly it. The light energy is absorbed by the intracellular and extracellular water, and it converts instantly into thermal energy.
Wow.
Yeah, so the laser creates these microscopic vertical channels of thermal injury. It basically vaporizes columns of the epidermis and causes highly controlled thermal damage deeper in the dermis.
But it intentionally leaves healthy, untouched tissue surrounding these columns to assist in the recovery, right?
Exactly. It's fractional.
So if I'm understanding this, it's like a home renovation. You have to take a sledgehammer to the old, damaged drywall before you can put up new, pristine walls.
That's a great way to look at it.
Yeah.
You are forcing the local dermal appendages, like the sweat glands and hair follicles, to rapidly resurface the top layer of the skin. And down in the dermis, that thermal heat acts as an alarm bell for the fibroblasts, which are the main factory cells of the skin. It forces them to start producing new collagen, which is a process called neocollagenesis.
But isn't this massive thermal trauma incredibly stressful for the cells? I mean, boiling the water inside a cell sounds like a catastrophic, potentially lethal event.
Oh, it pushes the cell to the absolute brink of apoptosis, or programmed cell death. But that extreme thermal stress is exactly what initiates the epigenetic shifts the treatment relies on.
And this is where the genetic database source comes in, right? The data on the HSPA4 gene.
Yes, exactly. So HSPA4 stands for heat shock 70 kilodalton protein 4.
Okay, so when the water inside the cell boils, the physical structures of the cell are compromised.
Highly compromised.
Right, so the proteins inside that cell, which need highly specific three-dimensional shapes to function, they start to denature, they unravel. I always think of it like an egg white changing from clear to solid white when it hits a hot frying pan.
That is the perfect analogy. And if those unraveled proteins are allowed to clump together in the cell, they form toxic aggregates and the cell dies.
Ouch.
Right. But the HSPA4 gene senses this extreme thermal crisis and immediately upregulates the production of these 70 kilodalton heat shock proteins.
And what do those proteins actually do?
They act as molecular chaperones. They physically bind to the exposed, sticky regions of those unraveled proteins, preventing them from clumping.
Oh, wow, so they hold them steady.
Exactly. They hold them steady, giving them a chance to refold correctly once the thermal heat dissipates.
So the laser isn't just burning tissue, it's actively forcing the cell's DNA to change its behavior in real time just to survive the crisis.
It goes beyond just survival, actually. The thermal energy from the EBD therapy actually modulates wider epigenetic changes.
Like what?
Well, the localized trauma triggers DNA methylation processes that effectively silence certain genes associated with skin aging.
Wait, really? It silences aging genes?
Yes, and simultaneously it attenuates the expression of matrix metalloproteinases, or MMPs.
Remind us what MMPs do.
They are the enzymes responsible for breaking down your existing collagen. So you are shocking the cell into a highly active, highly protective state.
Okay, but this raises a big question for me. If the cell requires an enormous amount of biological energy to manufacture these chaperone proteins and execute these genetic shifts, what happens when a patient is older?
Or if their skin is metabolically exhausted from years of sun damage, yeah.
Right. You induce this massive crisis, you ring the biological alarm bell, but the cell simply doesn't have the ATP, the cellular energy, to mount the response.
This raises an important question, and it's actually the hard limitation of traditional laser monotherapy.
Okay.
If the tissue is metabolically depleted, the HSPA4 response is weak. The neocollagenesis basically fails to outpace the damage.
And for you, the patient, this translates clinically to what? Prolonged downtime?
Exactly. The skin remains aggressively red for weeks, which is a state of prolonged erythema. Or, in a desperate attempt to protect itself from the unmanaged inflammation, the skin triggers an overproduction of melanin.
Resulting in post-inflammatory hyperpigmentation, or PIH.
You got it.
Yep.
The tissue is essentially stuck in the trauma phase.
Which means if the laser creates a massive localized energy crisis, the only way to avoid that stalled healing is to somehow subsidize the energy cost for the cells.
Right, we have to provide the building materials so the cell doesn't have to manufacture them from scratch.
And our sources point to polynucleotides as that exact subsidy.
Yes. The clinical literature refers to them as PNs, or PDRN, polydeoxyribonucleotide.
Which are highly purified fractionated DNA chains.
Exactly.
And the sources are very clear on the origin here. These are derived primarily from the reproductive material, specifically the sperm, of salmon or trout.
Right.
Which sounds wild on the surface, but the biological reasoning is that the DNA structure of these specific marine sources is remarkably similar to human DNA.
It's highly biocompatible. And the extraction process purifies it to such a degree that all allergenic proteins and active immune triggers are stripped away.
So you're left with pure, biologically neutral genetic raw material.
Exactly.
Yeah.
And we should also clarify how these function mechanically in the tissue, because they're often conflated with traditional dermal fillers,
Right.
like cross-linked hyaluronic acid.
Oh, right. They don't just sit in the skin to add volume, do they?
No, not at all.
No.
Polynucleotides do not sit inertly in the dermis to push up wrinkles. They are active biostimulators.
Okay, so how do they stimulate?
They engage with the cellular machinery through two very distinct mechanisms. The first is what we call the salvage pathway.
Let's unpack the salvage pathway because this solves the energy crisis we just talked about.
Right.
When the laser hits and vaporizes those columns of tissue, the surviving fibroblasts suddenly have to divide and multiply rapidly to fill in the gaps.
And cell division requires a staggering amount of DNA and RNA to replicate the cell's genetic material.
Okay.
Under normal conditions, a fibroblast has to synthesize these nucleotide bases, adenine, guanine, cytosine, and thymine, entirely from scratch.
Oh, wow.
Yeah, this is a process called de novo synthesis. It requires a massive expenditure of cellular ATP. It is slow, metabolically expensive work for a cell that is already fighting to survive thermal shock.
Here's where it gets really interesting. It's like instead of making a construction crew manufacture their own bricks on site, mining their own clay and firing it, you just back a dump truck full of pre-made bricks up to the loading dock.
That's spot on. It saves them a massive amount of cellular energy. The breakdown of the injected polynucleotide chains in the extracellular space releases these free, pre-made nucleotides.
So the thermally stressed fibroblasts literally scavenge these fragments from their environment.
They do. They bypass the metabolically expensive de novo synthesis phase completely. They pull these salvaged bases directly into their own DNA replication and repair cycles.
So the cell conserves its ATP.
Exactly, allowing it to dedicate its energy resources to producing collagen rather than just trying to copy its own blueprints.
So the salvage pathway handles the physical raw materials, but the sources also detail an active signaling process, the second mechanism. The polynucleotides don't just act as passive building blocks, they actually dock into specific receptors on the cell surface, specifically the adenosine A2A receptor.
Right. When the polynucleotide fragments bind to the A2A receptor on the fibroblast membrane, it triggers a profound intracellular signaling cascade heavily involving cyclic AMP.
And what does that cascade actually do?
This signaling pathway specifically reaches into the nucleus and upregulates the COL1A1 and CONA2 genes.
Which are the genes responsible for producing type I collagen.
Exactly.
And that distinction matters immensely, doesn't it? Because type I collagen is the thick, highly organized, basket-weave structural scaffolding of healthy, youthful skin.
It is vastly superior to type 3 collagen, which is the thinner, more rigid, parallel-aligned collagen that the body typically rushes to produce when forming scar tissue.
So the A2A receptor activation skews the factory output toward the highest quality structural proteins.
Right, and it also increases the production of elastin. Furthermore, this specific receptor engagement stimulates vascular endothelial growth factor, or VEGF.
So we are triggering angiogenesis, the formation of new microscopic capillary networks.
Which makes sense, because if we are demanding that the tissue build massive amounts of new type I collagen to heal a laser burn, we have to build the local blood supply to deliver the oxygen required for that labor.
And tying it back to the epigenetic shifts we discussed earlier, the A2A receptor signaling actively suppresses those matrix metalloproteinases, the enzymes that degrade collagen.
You are simultaneously accelerating the assembly line while locking the doors against the demolition crew.
I love that. But there is a physical physics problem we have to address here.
Oh, the molecule size?
Yeah. Polynucleotide molecules are macromolecules. They are relatively large. If you were to just apply a highly concentrated PDRN serum to intact skin, it would largely just sit on the surface.
Right, it struggles to penetrate the stratum corneum, the skin's protective outer barrier.
Which is precisely why combining them with fractional EBD therapy is so mechanically elegant.
Because the laser just drilled thousands of microscopic vertical shafts through that barrier.
Exactly. The laser creates the exact delivery channels required for these large hydrophilic DNA molecules to flood the deep dermal layers.
Though it's worth noting, the sources mentioned clinicians will often inject the PNs directly into the deep tissue with a needle immediately following the laser too, just to ensure absolute multi-layered saturation.
Makes sense. But this brings up a massive contradiction in the clinical literature that I really want to reconcile here.
Okay, let's hear it.
We know that the body's wound healing cascade strictly relies on inflammation.
It does. Acute inflammation is the initial signal that draws immune cells to the site of an injury to clear cellular debris and trigger the fibroblasts.
Right. So the laser creates a controlled burn to trigger that exact inflammatory response. However, our sources clearly state that polynucleotides exert a heavy anti-inflammatory effect.
They do.
Wait, if the laser creates a wound and the wound healing cascade relies on inflammation to trigger repair, aren't we blunting the laser's effectiveness by applying an anti-inflammatory DNA serum? Aren't we hitting the accelerator and the brakes at the exact same time?
It seems contradictory, I know. But what's fascinating here is the difference between acute and chronic inflammation. Polynucleotides do not stop the initial acute repair cascade.
Okay, so what do?
They tightly regulate it so it doesn't spiral out of control.
How does that regulation actually work at a chemical level?
Well, when a laser hits the skin, the immune system typically overreacts. It floods the area with aggressive pro-inflammatory cytokines, specifically tumor necrosis factor alpha, or TNF-alpha, and interleukin-6, or IL-6.
Okay.
If left unchecked, these cytokines keep the local macrophages, the cleanup cells, in a highly aggressive destructive state.
And that chronic loop leads to that prolonged redness we talked about, the breakdown of existing collagen, and eventually fibrosis or scarring.
Exactly.
So it's like the fire department shows up to put out the fire, but they just keep spraying the house with high-pressure water for weeks until the foundation rots.
That is perfectly said. Now, when the polynucleotides activate that A2A receptor, it alters the cytokine profile of the entire environment.
Oh.
The signaling strongly inhibits the production of TNF-alpha and IL-6, while simultaneously activating interleukin-10, or IL-10.
And IL-10 is an anti-inflammatory, right?
Yes, it's a potent anti-inflammatory pro-resolving cytokine. It actively binds to the receptors on those aggressive macrophages and forces them to change their polarization.
Oh, wow.
Yeah, it shifts them from a destructive state into a rebuilding, regenerative state.
So it effectively acts as a biological traffic cop. It allows the initial alarm bell to ring, but then it steps in, shuts down the destructive inflammatory loop, and forcefully pushes the tissue straight into the remodeling phase.
Exactly. And we can see the sheer power of this in the clinical trials provided in the sources.
Yeah, the data on treating stria distensae, which are stretch marks, and atrophic acne scars, is incredibly revealing.
Because both conditions are notoriously difficult to treat. A stretch mark is essentially an area where the dermal elastin fibers have physically snapped under tension.
Right.
And an atrophic acne scar is a crater where the tissue has essentially given up and trapped itself in a fibrotic, scarred state.
So in these split-face and comparative trials, researchers tested fractional CO2 laser monotherapy on one side of the face against the exact same laser combined with polynucleotide application on the other side.
And because it's a split-face trial, it removes all the variables of the patient's diet, age, or systemic immune function.
It isolates just the treatment protocol.
Exactly. And the combined therapy demonstrated a vastly superior rate of reepithelialization.
Which is the speed at which the skin physically closes over the microscopic laser wounds, right?
Yes. The clinical healing times were reduced by an average of 2.5 days.
Which, I mean, if you are a patient hiding in your house because your face looks like a grid of severe sunburns, peeling 2.5 days off your recovery time is an absolute game changer for quality of life.
Oh, absolutely. But it's not just about healing faster. The structural results of the collagen remodeling were significantly better.
Right. In the atrophic acne scar trials, researchers utilized the ECCA grading scale.
Right, which is a highly specific metric that measures the physical depth, type, and architecture of the scar tissue.
And the group that received the fractional laser plus the polynucleotides showed a statistically profound reduction in the ECCA scores compared to the laser alone. The craters actually shallowed out.
The rough texture smoothed over.
Because the fibroblasts finally had the salvage pathway materials and the A2A receptor signaling required to physically fill in those dermal voids.
They weren't just desperately trying to heal the new laser burn. They had a surplus of energy and materials to remodel the underlying historical scar tissue.
So combining the laser and the DNA simultaneously is highly effective. But the aesthetic clinic protocols in our sources introduce a newer paradigm that totally upends the timeline.
Yes, this is really cutting-edge stuff.
Right. If the DNA provides the building materials and energy for the demolition, what if we don't wait for the demolition to happen before we supply them? Let's look at the concept of priming.
Priming is where the regenerative aesthetics field is currently breaking new ground.
Right.
The protocol involves injecting the dermis with polynucleotides 3 to 4 weeks before you ever fire the CO2 or erbium laser.
So what does this all mean for you, the listener? It makes perfect sense if you think about running a marathon.
Oh, good analogy.
Yeah, you wouldn't ask someone who has been sitting on the couch for a decade to suddenly sprint 26 miles.
All right.
Right, you have to condition them first. You build up their glycogen stores.
Exactly. The priming protocol is essentially conditioning the cellular matrix to survive and leverage the laser.
We are conditioning the skin to survive the laser.
Right. That conditioning alters the physical and biological reality of the dermis during that 4-week wait. When you inject PNs into resting, uninjured tissue, they don't just metabolize instantly.
What do?
They form a viscoelastic three-dimensional scaffold in the dermal layer. And because these macromolecules are highly hydrophilic, they pull massive amounts of water into the extracellular matrix.
So the tissue becomes physically thicker, more hydrated, and structurally organized.
But more importantly, it becomes metabolically active and primed. The A2A receptors are engaged well before the trauma occurs. By the time the patient returns to the clinic a month later, their fibroblasts have already increased their mitochondrial density. They have built more cellular engines.
And furthermore, they begin to stockpile P53 proteins, right?
Yes.
And P53 is often called the guardian of the genome. It's the protein that monitors for DNA damage and decides whether a cell repairs itself or self-destructs.
Exactly. Having a massive surplus of P53 proteins readily available means that when the thermal shock of the laser finally hits, the cells have the immediate regulatory capacity to manage the DNA damage without panicking into apoptosis.
The laser isn't hitting dehydrated, metabolically exhausted tissue.
No, it is striking a robust, cellularly optimized environment that has been stockpiling raw materials for a month.
So when the thermal injury forces that epigenetic shift we talked about earlier, the resulting cascade isn't just additive. It's not simply like the laser's baseline result plus the polynucleotides baseline result.
No, it is entirely synergistic. The primed skin responds to the thermal trauma with a much more aggressive, highly organized, and sustained type I collagen response than unprimed skin could ever biologically achieve.
It completely reframes how we view skin rejuvenation. For decades, the industry standard was essentially just burn the tissue and hope it finds the energy to heal.
Right, cross your fingers and wait.
Yeah. But now we've moved from that to a highly sophisticated biological synergy. We are intentionally inflicting a micro wound, yes, but we are simultaneously feeding the exact genetic building blocks needed to rebuild it stronger.
We are preemptively altering the tissue architecture.
Bypassing cellular exhaustion via the salvage pathway, and actively dictating the inflammatory response via IL-10 so the body rebuilds rather than scarring.
We are no longer limited by the patient's existing, potentially compromised healing capacity. We have the biological tools to actively upgrade their cellular machinery before we ever introduce the stressor.
That's incredible.
And if we extrapolate this biological reality outward,
What do you mean?
well, if connecting adenosine receptors with external DNA fragments can so radically alter how our skin responds to thermal trauma, what might happen if we apply this exact priming and salvage paradigm to repairing deeper internal organs?
Wow.
Or, say, joint cartilage before major surgeries? Imagine injecting these specific polynucleotide sequences into a patient's degraded joint or organ tissue weeks before a highly invasive surgery.
Preloading the surgical site.
Exactly. If we can preload the tissue with the raw DNA materials and force the local macrophages into a regenerative IL-10 state before the surgeon's scalpel ever makes a cut, are we looking at the future of all human tissue repair?
That is a staggering thought to leave on. From erasing acne scars to potentially revolutionizing how internal organs recover from surgical trauma, it forces you to look at that controlled burn in a totally different light. If you condition the soil and drop the right seeds beforehand, the fire is no longer a crisis. It is just the catalyst for a much stronger ecosystem. Thank you for joining us on this deep dive. Keep questioning the established consensus, keep looking past the surface level, and keep exploring the incredible biological machinery operating right beneath your own skin.